Okay, so this is a video about 4.1, which is about maximum values, minimum values. So, yeah, let me explain these words. Maxima is just the plural of maximum. We don't say maximums, we say maxima. And similarly, minima is the plural of minimum. Extrema is just a word that could mean either a maximum or a minimum. If you think about it, maximum and minimum are kind of similar. It's just an extremely large value or an extremely small value. So we can lump them together and call them all extrema. They're extreme values, whether they're extremely large or extremely small. Um, so here's a definition. We say a function f takes an absolute maximum at a particular value of x if f of that value, say f of c, is greater than or equal to f of x for all values x that are in the domain. We say the value of the absolute maximum is f of c. Now, similarly, you'll see in red, I've defined an absolute minimum. Absolute minimum just means that f of c is less than or equal to f of x for all x in the domain. So f takes a local maximum if f of c is greater than or equal to f of x for all x that are just in some open neighborhood containing c. What is the difference between absolute maximum and local maximum? The difference is the absolute maximum requires f of c to be greater than or equal to f of x for all x, like ever, for all x in the domain at all. To be a local maximum, it just needs to be greater than or equal to f of x for all x in some open neighborhood, not necessarily all values of x, but just some open neighborhood, so values of x that are close to c. So that's the difference. And of course, similarly, there's a local minimum, and that's defined in red, and the only difference is that this inequality goes the other direction. So here's a picture just to illustrate the concept of like absolute versus local. I drew a graph, and this graph has some high points and some low points. This one, at least, it looks like a low point. It's not the lowest point ever. This point is lower. But this is the lowest point in some interval. Like if I draw like an interval containing this value of x, this is the lowest point within that little window. So I would say this is a local min. This one is the lowest point ever. This would be an absolute min. Similarly, we can, and I see another local min here. And then I see a couple of high points. So this one looks like the highest point ever, so I'll call this the absolute max. I'll call this one a local max. Okay. It's also possible for some weird things to happen. Like maybe I'll look at this graph on the right first. This one has a bunch of local maxes and local mins. Like here's a local max here, also here, here. It's like too many of them to really draw. Well, okay, it's not too many. All of these humps are local maxes. And then all of these upside down humps are local mins. Um, this one does not, I mean, at least assuming that it keeps doing this forever, like it goes up and up and up, and it keeps having this like humpy pattern, I would say this has no absolute max. Because if I go farther and farther to the right, it goes up and up and up. That there's no stopping to how far up it's going to go. Of course, it goes down a little bit, but then it goes up even more, and then down a little bit, and then up even more. But the point is, there's no highest point. I can always see a higher point if by just moving farther to the right. Similarly, there's no lowest point either. If I just move farther to the left, I can always find a lower point. So these things that we're talking about, they don't always exist. There's not always such a thing as an absolute max or an absolute min. In fact, there isn't always such a thing as even a local max or a local min. For example, this graph, this has no local max and no local min. Yeah. So that's what these things that we're talking about are. And now let's start talking about how to use calculus to find them. Oh, actually, before let me make a point here. Every absolute max or min is a local max or min, but not the other way around. I mean, let's just look at this picture. This absolute max is also a local max, right? Because, I mean, it doesn't really matter. I can draw a little neighborhood, and of course, this is the highest point ever. So, of course, this is also going to be the highest point in whatever neighborhood I draw. And to be an absolute max, that means you're automatically a local max. If you're the highest point ever, then you're also the highest point in the neighborhood. Similarly, if you're the absolute min, then you're also a local min. However, we see several local mins, like this one and this one, that are not absolute mins, and here's a local max that is not an absolute max. Okay. So now, let's talk about how to find local extrema. A local extremum has to be a point where either the function has a zero derivative or the derivative is undefined. And a value c such that one of those two things happens, either the derivative is zero or it's undefined, we call those critical numbers. So here's a picture illustrating this theorem. Here's a function that has a local max and a local min. And the way I've drawn this one, it looks like, let's talk about the derivative. This looks like a horizontal tangent line. This is illustrating the possibility that f prime is zero, right? A horizontal line has a slope of zero, and the slope of the tangent line is the derivative. So these are points where the derivative is zero. Here, I drew kind of a jerky function that has these sort of pointy corners. And we recognize this is the type of picture of a function that is not differentiable. A graph is not going to be differentiable at a point where it has a corner like this. This is like the graph of absolute value of x has a corner that kind of looks like this. But really any graph that has a corner is not differentiable. So, but in any case, this would still be a local min, because it's the lowest point, at least in a neighborhood around it. It's not the lowest point ever, because if I go down here, I can find a lower point than this. but this is still a local min, sorry. But it is not differentiable, and that's illustrating the other possibility, that f prime of c cannot exist. Of course, similarly, this one we would call a local max, and this is another non-differentiable point because the graph has a corner here. Okay, so let's do the following. There's several problems like this in the online homework. This is an important skill. I'm going to give you a function and an interval and tell you to find the absolute extrema for this function on this interval. I'll walk you through the steps. Step 1 is to find any critical numbers. So once again, what is a critical number? A critical number is when the derivative is 0 or undefined. So we find the derivative. Right? A critical number is where this is 0 or undefined. So I set this equal to 0, and I'll solve it for x. Everything's a multiple of 3, so if I divide it by 3, I get this, and luckily I can factor this. X plus 4, x minus 2. So x is negative 4 or 2. So I found two critical numbers. I have to check something else though, and this is a very common thing to forget. When you're finding the critical numbers, the first thing you do, or this isn't necessarily the first thing you do, but you set the derivative equal to 0 and you solve for it. A lot of people remember to do that, but then they forget to check whether the derivative is ever undefined. The truth is, probably the first possibility is the most relevant most of the time. For example, in this case, the derivative is always defined. If you look at the formula for the derivative, there's nothing here that would cause it to be undefined. There's no division. Like, what I'm looking for is domain restrictions. A domain restriction would include something like dividing by 0 or taking the logarithm of 0, some things like that. But this is just a polynomial, and polynomials have a domain of everything, all real numbers. So this derivative is never undefined. However, you're going to run into some functions where the derivative is undefined, and you'll have to remember that so you'll get all your critical points. Sometimes you will get critical points by looking at this. In this case, we didn't. We found all our critical points up here. So, yeah. And then step 2 is to test all your critical points and endpoints. What does this mean? When I say test, I just mean plug in some numbers. I'm going to plug in 4 numbers here. Two of them are going to be my endpoints. I'm trying to put them in order. That's why I'm putting this one first and this one last. And then 2 of them will be my critical numbers, like that. And now I just have to plug these numbers in.